So today we're in the middle of chapter 25, which is the next chapter that's not on your midterm, right? I just sent an email this morning to request that you guys send me your top question from each chapter, 22, 23, 24, by tomorrow 5 p.m. and that way I can do the midterm review Thursday. Does that make sense? So everything's just got pushed back. Yeah, if you didn't get an email from me, send me an email, and that way I can add you to the email list, or I just didn't type the email out correctly. So hopefully that gets resolved. And what else? Still no updates on the situation. If you guys know anything, let me know. But for now, what we're going to do is just work on the assumption that we're not going to get, Canvas and my CSU stand, all that stuff back, at least for until the midterm, which is going to be next Monday, right? Is that okay? All right. But we'll do a review on it on Thursday. And that way, everything just kind of got shifted back a few days just because to give you guys time, well, give me time to adjust also, okay? So today we have a little worksheet, but I want to go through a couple of more examples and a couple of concepts that before we jump into the worksheet. But as usual, let's talk about one interesting scientist today who was born yesterday, but we had two who was born on February 20th, but it's okay. We'll talk about her today. Kay Wei, who's actually a nuclear physicist, and she was actually part of the Manhattan Project, where she worked in basically developing, she's part of making the nuclear bomb that, I don't know, some can argue was, overall bad, overall good, right? We don't need to get into that. But her work was essential in nuclear fission, right, which is where you split larger atoms up into smaller atoms to release energy. So in this case, uranium and plutonium were the first ones we split in order to, well, there was not so nice motivation behind that initially, but then, nuclear fusion, I think it does provide about 5% of our power in the U.S., the electrical power grid. Okay, so it is, and we can figure out, we can argue whether or not that's a good idea, bad idea to have all this fusion waste afterward. Okay, but yeah, she was born on February 20th, 1902, and she actually went on to be a professor at Duke University in 1968. She passed away, 1995, before you guys were even around. But her work was essential in basically us splitting up the atoms and also providing energy for some of the power that we're using today. Okay, before I get started today, there's also a second announcement. So on Friday, in this same room, we're going to have our physical sciences seminar. We'll see how regular this becomes, because I invited multiple people, but they, everybody's just, saying, okay, we'll see what the schedule looks like in a couple of weeks. But this Friday, we do have Thomas Hanesco, who's a staff scientist at NASA. So he actually lives in Maryland in the Goddard, next to Goddard Space Flight Center. He's a research physical scientist, or that's his department, I think, but he does atmospheric science. So that's the work that some of you guys already know that I do. So I highly encourage you guys to attend. Here's the abstract. I'm going to have like these posters up around the hallway anyway, so you can read that. But if you are free on Friday at 2, please come by, and I'll have some of the students buy like cheap pizza and some sodas, right? So it's nothing fancy, but feel free to come by if you want to hear him talk about his work and how we're going to actually install some of these instruments on the roof of Naragi this semester. Okay. All right, so let's get started on the chapter 25 stuff, okay? Last time, right, we derived this little equation here where this is the potential energy between 2-point charges. If you have charge A, right, and then you bring charge B from infinitely far away, some distance Ri between the two, so that way, because the reason this requires energy is that these two charges are going to repel each other, right? It's like trying to push a spring closer and closer to compressing a spring. So as you move the charge closer and closer together, they're going to repel each other more, okay? And since you're applying a force to overcome the electric force, you're actually doing work on charge number 2 in order to bring them together. And when you do work on a system, you change the energy of the system. Specifically, in this case, we're changing the potential energy of the system, right? So the potential energy between charge 1 and 2 for two charges, right, is this 1/4 pi epsilon naught thing, right? Whenever you see 1/4 pi epsilon naught, right, you can just replace that with k if you want to simplify the calculation. But it's multiplied by the product of the two charges divided by r. And notice there's no absolute value sign in this case, right? If the two signs are the same, what happens? You end up with a positive potential energy. That's what this blue graph is showing you, right? As r goes to 0, it actually goes to infinity, right? But if the charges are opposite signed, right, then, right, negative times a positive will give you a negative number. So you have a negative potential energy, okay? Where instead of a energy that's going from, so this is a 0 of the potential energy, right? It actually starts off as, slightly negative. It just gets more and more and more and more negative as you go to r equal to 0, okay? It's like falling into like an infinite well in this case, okay? So let's see what happens if we have this case in this example where, let's say we have an electron, right, that is orbiting, around a hydrogen nucleus bounded by this thing called an electric force, okay? And the question asks you, how much energy does it take to ionize the atom? So this is something that's, it's like we haven't really talked about yet, right? What's ionization, right? So let's try to draw what's going on here first, right, in the setup of the problem, right? We have a hydrogen nucleus, right? So let's just make that. And we know that the hydrogen has one proton in this nucleus. And then there's some electrons that's actually kind of buzzing around, right? And the reason it's kind of wiggly because it's actually more of a cloud versus, something that it's not like a planet that just goes around in a circle. But, right? But we can model it as an electron that's orbiting around the proton at 1.0 angstrom. So let's call that R final, okay? R final equals to, well, an angstrom is actually 10 to the minus 10 meters, right? So let me just do that conversion there. So usually when you write angstrom, there's an A with a little circle on top of it. It's kind of like a Jesus A. Sorry if I offended anyone. 1.0, so I've converted that to my SI units, right, 10 to the minus 10, right, because 1 angstrom is 10 to the minus 10 meters, okay? Right? So we have a positive charge here, a negative charge here, so there's two charges, right? Let's call this Q1 and this one Q2, right? Q1 is a proton, so it has a positive 1.02 times 10 to the negative 19 coulomb. This should have been a negative here. Q2 is an electron, so therefore it actually has the same charge but opposite sign, right? Okay, so in this situation, right, if we want to ionize the electron, meaning just basically remove this electron from this atom and then, throw it off somewhere, okay? Basically, you're removing this electron from this atom, okay? That means what's happening is that these the electrons and the proton was actually bound together with some potential energy, okay? In order for you to ionize it, you have to actually add all that negative, remove all that negative energy by adding energy to the system and basically bringing the electron out to infinity, okay? Okay. So in this case, right, we need to calculate the potential energy of the proton electron system, right? And that's going to be this 1 over 4 pi epsilon naught thing, okay? Q1 times Q2 over R final without a square, okay? Okay. I'm going to replace this with just K, right? K is just 8.987 times 10 to the 9, okay, in SI units, okay? And then we're going to plug in all these numbers here, okay? 8.987 times 10 to the 9. So it's in SI units, and then I have to do the two charges, right? One of them is going to be negative 1.02 times 10 to the negative 19. One of them is going to be positive 1.602. Sorry, I said 1.02. 1.602 times 10 to the negative 19. Both have units of Coulomb, so I'm going to skip all the units for now, right? And then angstrom is 1.06 times 10 to the negative 10 meters. Okay. So that's the potential energy that is actually stored, right, between the electron and the proton. So let's calculate what that is. E to the 9 times 1.062 e to the negative 19 divided by 1.06, 10 to the negative 10, right? It's a very tiny amount of energy. It's 2.1. Let's do this. We're doing this to 3 sig figs, I guess. So I'm going to keep this intermediate value to 4 sig figs. Okay. So that's the value of the potential energy between the electron and the proton in joules. Okay. Okay. So what that means is that in order for, oops, there's a negative sign, right? Right, because there's opposite sign, so it's going to be a negative energy there. So in order for me to take this electron and take it out to infinity, you have to add exactly this much amount of energy, right? Equal and opposite of it, right? To make it so that the energy of the electron of the system is actually zero now, where they're not bound to each other, right? Okay. So the amount of energy needed to ionize is actually positive 2.176 times 10 to the negative 18 joules. But the problem asks you to convert this to this unit called electron volts, where electron volts is just a much more convenient unit when you're dealing with atoms and particles that are very low in energy, right? So I mean, it's a tiny bit of energy, but it's on a very small mass, right? So we want to use very smaller units than joules, okay? Because remember, a joule is just a 1 kilogram mass moving at 1 meters per second, right? So a 1 kilogram brick has many electrons in it, right? I don't even know what the number is, like probably 10 to the 40 or something. But I want to convert this to electron volts, and the conversion factor is given to you, right? Remember when you have conversion factors, right? You want to write the equation out for the conversion factor, right? And the magic is to divide one or the other, so you actually get the value 1. Let me go to the right here, right? If I divide both sides by electron volts, actually I'm going to divide both sides by joule. 1.062 times 10 to the negative 19 joule. I divide this side by the same thing, because that's just how my algebra will work, right? This actually cancel each other out, so you actually get 1. And remember, you can multiply any number by 1 without changing its value, right? So instead of multiplying this value by 1, I'm going to multiply by this ratio here, okay? 1 electron volt is the same thing as 1.062 times 10 to the negative 19 joules. The joules actually cancel out, and that's why I picked that way, okay? So when you do this calculation, you should end up with something like 13.5 electron volts. 0.602 e to the negative 19. Yep, you get 13.6. Oops, I cannot write 13. Sorry about that. 13.6 electron volts. Okay. All right, and that's the amount of energy that you need, in order to, if you just have a hydrogen floating around somewhere, in order to get that, take that electron and just give it enough energy so that it just flies off into infinity. Okay. Any questions about this example? Anyone seen this 13.6 EV number before from their other classes? Okay. All right. So I think this is known as a Rydberg. Because when people were first investigating this, they were surprised that, oh, you know, whenever you ionize an hydrogen, you get this number of energy out somehow. Okay. Okay. All right, so that's problem with two different charges, right? But as we all know, right, there can be more than two. What about three charges? What happens if you have three charges that you're bringing together? So once again, what I'm going to do is do the little drawing, right? Right. So I'm also going to deal with this where I'm moving the charge from on the x-axis, so we don't have to deal with the three-dimensional problem yet. Okay. The first charge you basically get for free, right? Because since there's no other charge in the universe, wherever you place the charge, it takes no energy, right? Because you're not fighting any repulsion yet, right? So that's Q1. Okay. So now, if I was to bring Q2 from very, very far away all the way out to, let's say, this distance x2, right? That requires, right, this amount of energy, right? 1/4πε0, the Q1 times Q2 divided by, instead of R1 is x2, right? That's the amount of energy it takes, right? If I was to bring a third charge, Q3, right? How many repulsion am I fighting now as opposed to just one? You have to fight both of them now, right? Okay. So now when we do this, let's say I put Q3 over here, right? Not only do you have to deal with Q1 repulsing Q3, I'm going to call that X13. You are also fighting the repulsion between 2 and 3, right? So that's X23. Okay. In fact, what I'm going to do is be consistent with my labeling. I'm going to also put a 1 right here. I can't erase that little part. Okay. Right. Okay. So this little notation here, right? 1, right, is the source of the repulsion. 2 is what the repulsion is acted upon, right? So X12 means the repulsion from one of Q2 due to Q1, right? X13 means the repulsion on charge number 3 due to charge number 1, and similarly, X23 is the repulsion due to on Q3 due to charge number 2, right? So now we have 3 different repulsion we're going to have to calculate, right? So instead of doing, so since energy is just a scalar value, meaning it doesn't have a direction at all, right? If it takes, you know, 3 different types, sets of energy in order to construct this, basically, this arrangement of charge, right? We can just add all the energies together, right? So what we're going to do, right, is to the total electric energy, potential energy, right? It's just the potential energy between charge 1 and 2, plus the potential energy between charge 1 and 3, plus, don't forget, the potential energy between 2 and 3, right? There's 3 different repulsion that's creating this potential energy between them, okay? So if we fill in these values, right, I'm just going to bring the K in front, right? Instead of writing 1/4πε 3 times, okay? So this is going to be Q1, Q2 divided by X12, right? Does that make sense? Right? Because that's the potential energy between charge 1 and 2, right? That's the same result we had before, right? 1 and 3, it looks very similar. We just have to change the index from 2 to 3, right? 1, 3, x 1, 3. And then between 2 and 3, it's very similar, but we have between 2 and 3 instead, right? You see that? Okay. So this is for 3 charges, right? Notice that you have to also care about, the repulsion between 2 and 3, not just between 1 and 3, right? So in general, there's this complicated index version of it, right? You can notice that it's almost like that, where this sigma, right? Remember, it signifies a summation, meaning for all the indices I that's less than j, you're going to have to add up multiple terms. So if there were 3 charges, there'll be 1, 2, 3 terms here. If there are 4 charges, how many terms do you think there are? The pattern, yeah, it's going to be more complicated than that. Okay. So if I was to bring in a 4th charge here, right, place it over here, right, how many more repulsion am I adding? 3, right? So we started with 3 terms. You have to add another 3 if we have a 4th. Okay, so there's actually 6 terms. Okay, you can see how this problem grows out of control. In fact, it grows exponentially, right, as you increase it. Okay, we'll try to deal with 4 charges at most with these index version, but just we're not going to do more than 4. Okay, because it just turns into a lot of writing. If you do 5, 5 will be 4 more, right? So so there'll be like 10 different terms in this little summation thing. Okay, right. So below, I'm not sure why the book write it this way, but this K could have been brought out in front like the way I did it, but he likes, the book wrote it with the K inside, but it doesn't actually matter because it just, that K multiplies to every term, right? Okay. So let's do a slightly, there's some other examples in the textbook. I think I'm not going to go through these examples because I want to save time for the worksheets. Okay, but other examples in the textbook, let's say you have some charge, right? 2 charges and they approach each other, right? So you start off with some kinetic energy, right? So this is kinetic energy, right? Then it converts that kinetic energy into potential energy, right? That's just applying conservation energy problem. Okay. There are also other type of problem where instead of the 2 charges are flying towards each other, they fly away from each other, right? If they were to fly away from each other, how much energy, how much potential energy gets converted into kinetic energy of both of the, the negative charge and the positive charge. Okay. So all of these things. This requires you to say, oh, well, if the energy of the system is conserved, the initial and the final energy is the same, right? We're going to have some potential energy initial, some kinetic energy initial, right? That's going to be conserved, oops, not plus, right? Equal to the final potential energy plus the final kinetic energy, right? So we're just doing this balancing. Okay, remember it's always the sum of the 2 that's equal to each other, right? The kinetic energy can change, right? But as long as the same amount of change happen to the potential energy, right? All right. Let's see. Okay, and we're not going to deal with the dipole stuff. So we're skipping this section. Unfortunately, I posted that on Canvas. Right? So if you're reading this section, right, we're skipping basically all the dipole stuff from the textbook, okay? It's not that dipole is not important, but it's an extra thing that we don't need to cover unless we have to, okay? But I just want to talk a little bit about dipole because I think I mentioned this before. Dipole is actually how even these little projectors or your computer screen, this is how they work, is that these dipoles are actually what's called liquid crystal molecules, right? What happens is that when you apply an electric field to them, let's say if I apply electric field this way, what happens is that these molecules will line up along the electric field, right? When they line up with the electric field, light can actually pass through it. This is light, right? When they're just kind of randomly oriented, a lot of the light gets blocked, okay? So this is kind of cool where if you were to turn an LCD on, or a particular pixel on your LCD on, right, it'll become opaque, or actually the light will go through, so this is the amount of light. And when you stop the electric field, it actually becomes opaque. And this is actually how your liquid crystal display panel works that's on your computer, where each of these pixels has a little controller on it where it determines whether or not to turn on that electric field. If that electric field is on, then the molecules align, so it lets the light through. If not, then it doesn't. Okay, it blocks the light, and that's how it can actually control what color is showing on your computer screen. Okay, so that's all we're going to cover today. Tomorrow we'll start off with this electric potential thing, which is slightly different from electric potential energy.